Welcome back, everyone. And today we're going to continue on doing more generating textures. And in a previous video about this, we were dealing with single bit of noise. We're just using Perl noise to generate textures on the fly. Today we're going to do like real Perl noise, which is done with octaves. That this was originally was done to create different types of textures like marble and clouds and things like that. So the way real true Perl noise works is by using something called octaves. And octaves is a very simple concept. The concept of doing like octave noise is that you take different resolutions of the noise. That's really all it is. And you just combine them. So here's an example of a tool I put together a year ago to illustrate this, is that here's our Perl noise. It's just random noise that's kind of smoothed out. And the second, for every octave, you change the frequency and you change its amplitude. Its frequency is how you step through the noise, and amplitude is how tall and how low the overall arc is going to be. So this is, let's say this is like an amplitude of 1, and it steps through as like one step at a time. For the second octave, we are going to increase the frequency and lower the amplitude. So as you can see, the wave is shorter, but it's longer. But the wave is still there. So you have this up, down, and it kind of straights out, up, down, and straights out, and we continue forward. So like I said, we're changing its frequency, and by changing its frequency, we're actually zooming out from the actual noise. So we're taking a bigger picture of it in a shorter, in the same amount of space. So like I said, frequency is essentially controlling the zoom. You're zooming in or zooming out from the noise. And in octave 3, we zoom out even further. So we have that up, we have that down, the straighten, and we go back up. Where this one's about to come down, this is where it goes. It continues. So we're even zoomed even further in octave 3, and the amplitude is even shorter. So this is how visually how you can understand octave noise, is that you zoom out and you shrink the wavelength. And there's names for it too. There's linearity, and that is the value that increases frequency per octave. So right here I have a set for 1.6, and then you have persistence, and persistence changes the overall amplitude per octave. So where persistence shrinks amplitude, linearity increases frequency. So increasing frequency means I'm zooming out. Persistence, I'm lowering amplitude, means I'm shrinking the overall wave length of the Perl noise that you're going to get. And then at the very end, you combined everything. So, and there's like different ways to combine it too. I'm going to show you a couple different approaches about it, and each one gives you different results and gives you different types of textures and things like that. But yeah, as you can see, this wave, the overall wave exists in the final, but these two like kind of are applied to it. Like usually you add it or you average it or you do something, and the overall changes it. If you mess around with it some, you can change persistence a little higher. So you have just overall. So the idea is with Perl noise is that, let's say if you're going to use this to create terrains, this is the starting wavelength you have. After you do a couple of octaves, you end up having the wavelength transformed into this. And this is a more natural terrain look as opposed to this. Terrains aren't smoothly hilly like that, unless I guess you're in Ireland or something. But in real life, they're more rocky. So if you want to make more of a rocky terrain, octave noise is really your go-to choice, because it gives you some control of how rocky it is. Like I said, you can change the overall persistence. So you can really start off with some smooth, and then just by changing persistence, you can make it more and more rocky to the point that it's too crazy. So you can transform this into this insane waveform. And you can take this data at a per pixel level and then generate textures. So that's what we're going to do here. So this is what it looks like with low persistence, and this is what it looks like with high persistence. Persistence should be a value between 0 and 1, and linearity should be a value between 1 and infinity, really. Whatever value you want to try. The higher the number, the more noisy it gets, or more grainy. So that depends on, you experiment and see what you like. So let's look at some code. So now you kind of get the visual idea of what octaves and noise is all about. So I created a function from the previous video. We kind of had all this code dealing with frequency and everything else. I kind of just made a function, class that kind of abstracts a lot of that away, and I call it noise data. So this is not useful right now, but it passes in. You can pass in whatever noise functions. I can pass in simple X, or I can pass in Perlin, whatever you want. So the simple idea is that we're going to have to loop through every pixel in our image, and we want to grab some information. So we're going to say, hey, give me the octave at X and Y position. And then you save the value. This looks like this. This is the end result. This is what octave Perlin noise. It's 3 octaves. It has different things. So this is the octave. So 3, persistent 0.5, linearity 1.6, and a frequency of 1. If you change these values, you overall change the textures. So this is like probably the most simplest version, and this is what I'm using on that page. So you make a loop of octaves, and you're just grabbing a single sample of your noise. So you have your frequency and you have your amplitude. Very simple equation. And what you're going to do is add up your total amplitude. So for every time you apply amp, you add up the amps, and you also add up your total noise. And then at every loop, you decrease amplitude by multiplying it by persistence, and then you increase frequency by multiplying it by linearity. So linearity will increase it by 60% for every octave, and amplitude will shrink 50% at every octave. So by octave 2, it'll be 50% of 1. In the second loop, it will be 50% of 0.5, which would be like 0.25. So that it just keeps compounding. It's a power function. It's to the power of 2, power of 3. That's what we're doing with persistence and linearity. And so once you have your total noise and your total amplitude for all the octaves for in your one sample, you can just do kind of like a quick average. You kind of average it out based on how many amplitudes and noise. And like I said, that's what generates. So if you want, let's say we decide to change the values a little bit. So we increase the frequency, and now you can see things are different. Let me go back to that frequency. Let's change it to, let's do a frequency change of only 2% or 20%. And there you go. And like I said, the linearity and frequency control the zoom. So you're just zooming in and zooming out. Let's see, persistence is, let's do very, very little change of amplitude. If we click refresh, again, you get different results if you play around with it. And at the end, you can always play with it too. You can then continue further and continue processing your octave data. So that does that, and you can maybe do some smooth steps, which doesn't work for this instance, but maybe I have to do a multiplication. You click refresh, which doesn't work. Whatever. You got to play without. You can just play around with it. I don't want to play around with it too much today. Now, like I said, that's kind of like the simple way of doing it. There's another way you can go about it. So if we're going to go to, let's say, a different algorithm of how to do octaves. And here's the result. You get a whole different texture. We're going to use the exact same values. We're still going to use the same persistent, linearity, and frequency. But in this one, we're doing things a little differently. Let me keep them open. Now, the way these three lines of code work, excluding the amps, calling the function with the frequency and amplitude and doing the persistent linearity, these are the exact same thing as these two lines of code. The only difference is I'm using a POW function. Where this one I'm keeping track of amps and then modifying the amp at every loop. Same thing with frequency. I'm modifying those values. Instead of modifying those values for every loop, I'm calculating those values for every loop. So, linearity, use the POW function, and just so I have x, your base frequency times linearity. Same thing here. And persistence is that value, and we use the pound sign of the octave you're currently in. If you do a power function on, let's say, a value less than 1, you actually shrink the value. If you do a power function on something that's greater than 1, you increase the value. So it's kind of a neat trick to go about it. But I don't think this is the most efficient way of doing it, because if you're going, let's say, we're looping through 256 by 256 image, so you have a lot of pixels. So for every pixel, you're going to call this function, and then for every function, you're going to loop through this 3 times, based on, because you're looping it there. So that means you're calling a POW function 6 times per pixel. So that performance-wise, if you have to call another function, it slows things down by micron or whatever. It's really small. But when you're dealing with tons of calls, like thousands of calls, it kind of all adds up. So performance-wise, this might be easier. It's easier just to modify some memory as opposed to calling a bunch of functions that sets up its own memory and then modifies it and sends return value back and everything else. So I just want to show you a different approach. I would say this is more efficient. This one seems more mathematically fun, I guess, because you get to play with POW functions. I just wanted to show you that these are almost the same. So it's overall the way you do frequency and amplitude and you do the basic math for octaves is the same. It's how you combine it and how you the final result is what changes how the actual texture will look like. So in this instance, in this type of version, we're keeping track of the minimum and maximum value of n. So, and we add up the total n, total noise. So we're still doing the same thing. We're still saving total noise, but we're just saving it. But we're just keeping track of the minimum and maximum instead of keeping track of the total amplitude that's been added. When it's all said and done, you then take the total noise and then take noise min and max and you normalize it. So you normalize the single sample of octave noise. So you end up getting this result. Now for fun, you can add different things. So this one I'm going to do kind of like an average of total divided by 3 because I applied it to 3. By doing that, then normalizing it, you get a whole different result. So, so I have like lots of these get octave functions that we can play with, but ideally the best option to me in the long term would be to create a special get octave function that instead of doing these like final things for you, that maybe it returns all the values like total amplitude, minimum noise, maximum noise, total noise. So this way, at the very end, you can choose to modify it how you want. Like so, this way you can basically get raw octave noise, and then you apply your final massage to it any way you want. Like I say, you can do averaging. You can do this type of averaging. You can do normalizing, or you can do this averaging and that and noise. It gives you whole different results very quickly and very easily. So ideally, like I said, these are what ideally what people do. I think the best function to me would be something more flexible that allows you to continue on with massaging the data. But if you're just looking for example of octaves, and this is like I said, this is another good example of dealing with octave Perlin noise. This is not true Perlin noise exactly, but it's close to it. This is kind of like a single sample of Perlin noise. Now that leads us to something that's considered more the correct way of Perlin noise. Let's see, we're going to move on to texture 3. In this version, we're going to pass in the width and height instead of a frequency, instead of like the X and Y. And this gets back an array of data. Oops, go back to here. So what are we doing with? So we're using Octave 3. This is probably the more correct way of doing it. Get rid of those octaves. So we have Octave 3 as the final octave. Now, like I said, we're passing in the width and height of the texture. So this way, we're going to make an array of that size. I don't know why they say why. Why? Shouldn't it be? Oh, okay, that's why I'm doing. I'm doing, for every Y, I'm creating another array of X. Okay. So Octave 3 does things a little differently. It actually creates an array for every pixel in our texture. So if this is 200 by 256 by 256, it's that times that. That's how big the array is. So we're going to save a noise value for every single pixel in the image, right? So where 1 and 2 gives you a sample of a single slice of noise, just basically a single pixel of noise, Octave 3 gives you all the noise for the entire image, not just a single pixel. And the reason why is that you do something slightly different. This is like the same approach. I'm keeping track of all the values again, just like sample 1. Like I said, it's more efficient than calling POW functions. And again, we're keeping track of the minimum and maximum noise. And during the octaves, we add up the noise value, and then we save the noise value into that, I guess, pixel position in the array. When all said and done, we then go back and reloop everything, and we normalize everything. But we normalize it based on the value, the min and max of the entire image. Where Octave 2 gives you the normalization of the single pixel, this one, like I said, gives you normalization of all pixels. So this way, every pixel in the image will be a value between -1 and 1, plain and simply. And it'd be like it's the overall like perfect average. It's like the best way to do it because it gives you a certain effect that you can't do it in the other ways. And the result is a cloudy effect, and that's what Perlin noise. Perlin noise really is to really get you like kind of a cloudy thing. So this way you can do like marble and a bunch of other different types of textures. I don't know the algorithms to actually create marble and everything and to get the right values. But if you look it up, you can find different types of textures you can do with Perlin octave noise. Right here, I just want to play with it. But this is like the best approach. But at the same time, this requires a lot of pre-processing. So you got to process all the noise first, so you can then average, normalize the values based on all the data. But like I said, it gives you different textures. And let me change this to octave of 3. What does it look like? It's less blurry. Like the more octaves I apply, I think the less blurry the texture. It ends up having a little bit more detail added to it. But overall, like I said, we're using the exact same values for every form of octaves, and every approach gives you a final different types of textures. Like octave 1 and 2, you can kind of build these cell type of textures, or Octave 3 allows you to do more of a cloudy kind of effect. But like I said, this requires more pre-processing. And that's really the gist, like I said, and that's really just the gist of Perlin Octave noise. I think I have one more, which was just to play around with. This is just me processing the information. Like what I'm doing here is like I'm just taking that one pixel and just adding it. And like I said, you can mess around with it. Let's see what this looks like. Well, let me go back. Yeah, okay, it's still good. So that's me, taking that cloudy effect and then messing around with it. If I want, instead of using smooth step, I can do something like this. I don't know what this is doing. If it's a value greater than 4 or less than 6, you make it into 0. So it's kind of like smooth step but inverted. Click over. You create a whole different effect based on clouds. So yeah, you can end up creating some weird, funky effects. Like I said, you can play around with it. Let's see what happens if I do this. I forget what it is. Still keeps it cloudy. So doing that 0 is probably like the best. It's kind of neat. It's different. It gives a whole different effect going on. Let's see what the final play is. Let's see, texture 4, and I don't remember what texture looks like. And refresh. Ooh, wow. Oh, okay, that's cool. I totally forgot I did this. Okay, because I'm using a special thing, a color set palette. I probably used this in the past. There's a nice, really cool equation this guy created, and it's a shader code that allows you to pass in certain values, and it creates these really cool gradients. And he has a bunch of cool effects that uses these really cool gradients. And this is basically the overall shader function. So what I did is that I created this function in JavaScript. I ported it over to JavaScript, and so I'm able to use it. So let's see, what does it look like before I start adding all these color things? So yeah, I made it pixely. I think that's what I'm doing. Like with this function, I'm actually trying to take all the noise, and then I'm pixelating it. So I'm pixelating the noise, and when I'm done pixelating the noise, I then take the noise value. I don't know why I passed it. Did I have to pass X and Y in there? What did I do? Set palette X, Y. Where is X? Why am I using X, Y for? Index. Yeah, I don't remember why I'm using X and Y. Like I said, I just ported this over. I made sure it works. Oh, I'm setting the color. Okay, so this. Okay, that's what I'm telling it which pixel. Okay, this is the texture drawing function. I'm sorry, I totally forgot about this. So I'm telling which pixel to draw, and then I'm telling it the time, and then these like color parameters, and I just end up just calculating the exact indexes for the 4 colors, like RGBA, and just applying his math equation on all the colors. Just using A, B, C, in different positions. Like I said, this is kind of like the JavaScript version of this simple math equation that he has. And yeah, let's see what it looks like again. So yeah, I pixelated, and then I used his little color algorithm to add his funky gradients to it. And this is the final result. I totally forgot that I did this, to be honest. This was like 2 weeks ago. I'm finally making a video about it now. But yeah, there you go. This is a final example of Perl and noise using octaves. Like I said, you can be very creative with it. Like I said in text 3. Oops. Text 3 and text 4 is the same. Like I said, the only difference this is basically the cloudy effect when it's pixelated. So it's not that one. It's the one without all this fun stuff in it. It's without this. So it's really the pixelated version of this. So that's the difference between text 3 and text 4. I take this texture, like this, all the final processed information, and then I pixelate it. And the way you pixelate it is you just, for every when you loop through, you just loop through for every like square, you just grab the exact same pixel, and that's all I'm doing really. It's kind of a cheaty way. I think when you pixelate it, I think that's how you pixelate it. I'm not sure, but like I said, that's how I'm doing it. It's like, so for every grid of information, I'm just grabbing the exact same pixel of noise. So that's why I have like a floor X. And same thing with Y. So that's that part, and this part is what creates the right X and Y values. So no matter if I'm looping through width, I'm actually looping through width per like cell, like a giant cell, which is D. And what's D stand for? D is 6. So it's 6 pixels. For every 6 pixels, I'm combining it. So this way, every 6th pixel basically gets zoomed out. That's what I'm basically how I pixelated it, and like that set palette thing colors it. So yeah, that's really the gist of it. So that's it for texture generations. From now, after this, I want to do some more. I'm just not exactly sure how to go about it. So if you guys have any ideas of any other texture generations you want to do, there's tons of algorithms we can play with probably out there. You just tell me, and I'll see what we can do. I really want to still want to deal with animating, having some kind of animation so that you can see the noise kind of move, things like that. There's like things like that I still want to do. Changing the shape, instead of using a quad, have maybe a circle, so this way everything kind of goes around instead of up and down. This way you can create different effects that way too. Yeah. So so I'll please like and subscribe because the new YouTube video rules. I need more subscribers to keep certain features, and so I guess I'll see you guys at the next video. Thanks for watching.